Welcome to the Kaiser NeuroMap Masterclass. This is, I think, our third one this summer of 2021. We're doing them every 2 or 3 weeks. And we're going to start talking about the central nervous system's basics, the CNS. And we're going to start with the cell type, the ogliodentrocytes, that are responsible for the insulating of our axons in the brain that allows speed of communication between the cells. And I'm going to go just jump to the end before we start with the beginning. Just show over here on the right side. This is a typical neurofeedback trial using SMR, sensory motor rhythm training, and it was done at F4 and P4. And if you know where those sites are located at, they're right between. You see this is increased myelination. It's a DTI, what's called defensive tensor imaging view of the increase of myelination, and this is actually in kids going to college. So it wasn't like they're even having a problem, but you're adding with that neurofeedback because you're reinforcing the coordination between the two sites, and that results in attracting cells, attracting ogliodentrocytes. All right, it's okay. This and when I'm talking about the brain, we're going to sometimes we'll do like a side topic that gets us to where we're going, entry topic, I guess. And this one, we're talking about attention systems. I'm going to show you at least 3 attention systems that we know that we have in our head. One, we have the sentinel system. The sentinel system is the one that immediately detects that blue dot, immediately sees it. It doesn't take a moment to see it. The sentinel system is non-conscious, registers things in parallel. You could even call it pre-attentively, pre-conscious. Well, then we have the explorer system where we consciously have to direct our attention. And here we're looking for the black circle. It's actually in the same place of the grid, but it takes time because you're doing what's called a conjunction search. Here, boom, you found that. It took you 200 milliseconds. All right, where's the black circle? Let's find the black circle. Where did we put it? It's not over here. Is it hiding behind things? I don't even know where the black circle is. You can see the bigger the array, the longer time. Oh, there it is, right in front of me. For a moment, then it looks like I can see it. Once I get near seeing it, it's almost hit that sentinel system, recognizes it too. Okay, just continuing on in visual processing. So what we're looking at, non-conscious vision versus conscious vision with the attention. Now, this is a very old slide, but I can't find anything better. The one on top here that's showing the divisions of the visual information into the stimulus aspects of like color, motion, form, and depth. We're going to spend more time on vision, but just to, as long as we're talking about this attention, this is like a what's called a superior colliculus would detect most of that. And that's why we can see it so quickly. We get to our superior colliculus, I don't know, 30 milliseconds after the eye. It's very quick, maybe 20. It takes about 50 milliseconds to get to the thalamus and 90 to get to the cortex from the eye. We have some different pathways, and what you see in the brain is we have these different complementary systems, the more magno and parvo ones in the visual system. We'll talk about someday, but and you have a superior colliculus, this other more primitive one, that's the fish one that we use every day, every moment of the day, or not every moment, but like when we're driving and you're coming off and you're going on an off ramp, and you're about to hit that T junction, and you're gonna have to turn left, and suddenly you look, your eyes go right towards a car that's going to be crossing in front of you, and you need to wait for that car. Well, the reason why you don't have to really search, you can put your eyes right on that thing that's moving, is because your superior colliculus has been tracking it, has detected it, and that non-conscious vision is used, and it, in essence, gets the eyes prepped to go, where are you going? And then the conscious system kicks in. Now, what's most interesting about the superior colliculus, superior means on above, inferior colliculus means below. The most interesting, the inferior colliculus is actually our most important brain area. And how do we know this? Because the brain tells us in terms of its anatomy and also its function. The inferior colliculus, which sounds like some brain area that gets sand kicked in its face at the beach. But it's not inferior in any way. It is the one that gets more cerebral blood flow per cc per minute per unit time, cubic centimeters per unit time. You can see it's 1.8 in this data. This is in cats, and then you get the sensory motor strip, and then you get the auditory. That system is part of this. This is our sentinel and prepare system. The sentinel system is the inferior colliculus, and then your conscious system being able to discern, okay, what do they just detect? The sentinel, so the inferior colliculus is the non-conscious auditory processing. It's the one, like if someone makes a loud noise, loud sound, we're always mapping our environment with acoustically, unless we're deaf. In fact, when deaf individuals, often are using both their visual system for the sentinel features and the exploring features. But going back to our individuals who can hear, the inferior colliculus, again, here you can see has more glucose, more energy usage, and then the auditory second there, and has more capillary density, it's highest, and other density, glutamate. So very important area of our brain. It's the area that it's very sensitive to oxygen. You can see if it's getting that much blood flow, that passage, that throughput, it's going to be sensitive to when it loses that throughput. And you do have, anoxia events when you lose oxygen or hypoxia that can damage the inferior colliculus, sometimes right at birth. And as we age, it gets impaired. And the inferior colliculus is when a lot of people say I have trouble hearing. It isn't that they have trouble hearing in a pristine environment when it's all very quiet. It's that they have trouble hearing, shadowing one source of sound in a noisy environment. And it's the job of the inferior colliculus to do that shadowing. So a lot of times when people say they have trouble hearing it, it's not that they may lose some of their register, the range, but they're mostly talking about that inability to track one source, like a conversation, in a busy, noisy environment. And that's because the inferior colliculus has degraded over time, structurally, and thus functionally. Okay, here's another form of attention, the cerebellum. Cerebellum doesn't care about the cerebrum, what it thinks. And there's ways of showing this. I wish I had a video of this, but what they do is they use a optical illusion. If you look at these two colored discs or circles, looks like blue's much bigger. But that's an illusion. That's what our brain does. That's what our cortex is doing, because they're the same size. If you look at them now, they kind of look the same size now. Now the pink looks the same as blue, but no, the pink's much bigger. It's an optical illusion. Now when you do this optical illusion in real space, like with poker chips in discs, and when you go to pick up that center disc, your cerebellum ain't fooled. And they did the study here 26 years ago, and they measured with calipers the distance of your grip, and your fingers are going in to grab that chip. It's bigger here than it is here, even though our cortex says they're the same size. So our cerebellum helps adjust what's going on, and that is a different form of attention. So the cortex, the cerebrum, showing a different attentional system than the cerebellum. This is the brainstem attention system, in essence, the one that lets us see that quickly. And then let's move up into the cerebrum, into the cortex. And now the two hemispheres. Each hemisphere has its own attentional system. And what happens inside of a hemisphere is not available to the other hemisphere. There's a communication with corpus callosum I'm going to show you in a moment, but there's no real, it's picking the outputs from the other hemisphere. It doesn't have any access really to what's going on internally. And one of the ways this was studied is by doing a basic little test where you do a left hemisphere dominant task, such as recognizing an object like a chair, versus a right hemisphere task where you're recognizing the emotional expression. So you got object versus expression. And Ted Landison, 40 years ago, I think he was actually a student of my advisor, Ron Zidell, and working with Joe Bogan, probably, who was a surgeon working with split brains, which we're going to go into the hemispheres and the split brain patients in a later podcast or masterclass, a later masterclass. Okay, so what he did in this basic little test is I came in, I'm sorry, I forget when he came in. He published this, I came in about 7 years later, 1988, to this lab. While people are doing this task, they got a keyboard in front of them and they're seeing a screen and objects or whatever they're looking for is being thrown on the screen. And they hit like a Y for yes and N for no. And he noticed as people are doing this task, and you have them do like 300 of them, and they're coming one after the other, eventually the person, oops, sorry, I didn't mean to hit that button, boom, boom. And he would track how many times, what button they hit, and what they said, if they made any comments about what they were doing. And he tracked and found out when it was a left hemisphere task and they said wrong button and oops, they were pretty much 100% correct that they were wrong in hitting that button. But when they said wrong button, oops, and they were doing this right brain task, expressions recognition, they were pretty much at chance levels, showing that the speaking hemisphere, the left brain, had no access to what the right hemisphere was doing. Okay. All right, so we've all gone through lockdown, through COVID, and one of the things happens with social isolation, which most of us have experienced to some level, is our cells they shrink their processes. They lose their myelin, and we can see this very readily in when they look at rat studies. They have what's called the enriched condition, ER, the standard condition, where they have some other rats in their pen, but they're not. They don't have any toys, and the or things to do, and the isolated rat condition. So or impoverished. And what you do, we're gonna compare all three. Now, one thing I just want to say about the enriched condition, they have to change these toys about every 2 weeks, or they start getting closer to the standard condition, which is like I always like to give the advice: change things around in your waiting room for clinicians who are doing neurofeedback. The default network training in particular, keep things fresh. It's to help the brain keep increasing the neuroplasticity. Well, the ones who are in enriched condition, you can see has all these measures. They're much bigger in terms of cortical thickness and weight, and the corpus callosum, which is this wiring system, other things, and much better improved, more connectivity going on. And then you can see that's the anatomy improving, and even cells. Neurogenesis is usually near like the olfactory areas in the primitive part of our brain, none of the advanced parts typically. And hippocampus has some, but behavior. So the structure changes and gets improved, the behaviors follow, cognition follows. So we're going to be talking about this myelin, this insulating sheath, and we have the neurons have, and they have a dendritic receptive field, and they have an axonal terminals, which they connect with the dendrites, typically across a little gap, the synapse, which we're not going to go into today. But we're going to talk about this myelin, this fatty layer, this lipid layer that helps the transmission of the communication from this nucleus of the cell to other cells. And just to think of it, it's like it's why we don't get electrocuted when we pick up a wire, electrical wire that's plugged in, unless it's frayed, and then the electricity can come out to us, because the electricity wants to go every direction, in all directions, all dimensions, probably higher dimensions. It's trying to go everywhere. The insulating material doesn't give it a chance for anything to pass. It blocks it from passing on. And we use plastic and rubber and other materials. The brain uses these ogliodentrocytes. Ogliodentrocytes will wrap around an axon, limiting the spread of electrical chemical communication. In fact, without myelination, the axonal speed is only about 2 miles per hour. It can get up to 260 miles per hour with the axonal sheathing, the myelin sheathing, and it can also increase its refractory time, so it can communicate. It can send a new message. It doesn't have to wait till the message gets to the end. It can send it, like, I believe, after it passes each gap. It can send again if it needs to do so in its communication. So they're very important. One of the things it shows you in some respect in a larger scale, a lot of times I like to think I talk about how the brain and its workings reveal the cosmos. And one of the things is saying, if you have a message, it's not valuable if it just goes in all directions. It's got to connect with probably other cells that are in some reciprocal relationship with you. So you don't go out and scream to the world, to all people, some message. If you think it's going to be valuable, you tell the people that you have reciprocal relationships with, or who you can have some strong relationship, and you do this very closed communication. In fact, when cells like astrocytes start to die off, they'll start to communicating the same to all, kind of a dementia from the astrocytes. Okay, just a good, try to get a clear picture. It's all diagrams. Here's our neuron. Here's, I guess, an incoming precursor cell or ogliodentrocyte precursor, or maybe even a grown one. And it's creating a strong communication link between this neuron and whatever neurons have the dendrites attached over here. And this is, sorry for the sort of the quality here, but this is the best I could find on maturation and differentiation, just showing how we have these precursor cells, and they believe in some level the precursor cells are like Johnny Appleseed. They get spread by these progenitor cells that move around and create these basic cells. There's a progenitor there, and then the precursors are here, and they can be transformed. There's some interesting research that isn't really relevant to what we do, but it is a little bit interesting in how the idea that these precursor cells or progenitors can actually become neurons or astrocytes or stay ogliodentrocytes. But it looks like the data is a little bit mixed, so it's not definitively known yet. All right, this was this nice view again of this wrapping of this lipid layer that causes it's going to create insulation, so that the electrochemical gradient will stay within that sheathing. And here's another view of the precursor cells and getting to the ogliodentrocyte, full myelinating ones.
Wikipedia is the best thing ever. Anyone in the world can write anything they want about any subject, so you are getting the best possible information.
And I bring that up because I went to Wikipedia to see what they ogliodentrocytes, what they talked about there. So the progenitors or the precursor cells, same thing. One time I read that they were scattered everywhere, like they're already pre-sprinkled everywhere in the neocortex. And then as I was reading this morning, I was talking about these cells move around, and so like I said, like more like maybe like a dandelion seeds going everywhere. What is useful here? They provide that electrical insulation. I like the same thing, say electrochemical, to be clear about it. The loss or lack of ogliodentrocyte precursor cells, or the consequent lack of differentiated ogliodentrocytes associated with the loss of myelination and subsequent impairment of the neurological functions. So we are going to talk about demyelinating in a moment. They talk about, so the precursor cell is kind of like a leopard. Doesn't like leopards around it. This is kind of interesting. Where was this phrase that said this? OPCs have a remarkable homogenic distribution throughout the brain, like the sprinkles everywhere. This is achieved through active self-repulsion. They're like the same, like magnets, but they're all north, and they repel each other, causing the cells to be generally equally spaced from one to another. And there's the references if you want to follow it up. I assume it's, this is one of those things where you're trying to describe something, and it's probably true 90%. There's probably some places, some areas of the brain where that isn't true, but it's probably true for as much as you can sort of assess the brain, because the brain is almost like studying star systems. Even though they seem to be close to us, because they're so small, they're far away, and that's why we need microscopes. And it's hard to survey really what's truly completely what's there comprehensively. You take samples, and from the samples get your idea. So they're 3 to 4% of the gray matter and 8 to 9% in white matter. Okay. Making them the 4th largest group of glia after astrocytes, microglia, and ogliodentrocytes. Oh, they're talking about the precursor cells. I was wondering why the white matter was so low. Talking about the precursors. Okay, that will become the ogliodentrocytes. Okay. We got glutamate, fat to excite, and GABA to inhibit. Okay, let's see what else is going on. So that phrasing of repulsion reminded me of cosmological inflation, where things are just spreading out, because in a lot of ways our human life is we're a version of the cosmos. In fact, if you put us on a logarithmic scale of time, where Planck's time is the shortest amount, like -1 to the 43 seconds, I think, or something to that degree, up to the length of the universe. If you put us on log time, we live almost the length of the universe. But that's somewhat obviously how logarithmic transformations can somewhat mislead, but in the same way tells you something. So in a way, while all these cosmos is, we're here for how many years? 80 years, let's hope, or 90 or 100, or but our brain shows a process of inflation in a way that's similar to the cosmos somehow, but our systems are communicating with each other, unlike the galaxy, unless you talk gravity waves or something. Okay, OPCs have a remarkable, okay, that's what I just mentioned. Depth of differentiation of the OPC is rapidly followed by migration or local proliferation of a neighboring cell. So it's opportunistic. If the space opens up, we move in there. Okay, development. So they originate in this part of the spine, they said, neuroepithelium, and they migrate to other areas in the brain. That's why I show this migration going on. Several waves of OPC production and migration lead to a generation of ogliodentrocytes, and these precursor cells are highly proliferate, migratory, and bipolar means they, got trunks on both sides, an axon usually in a dendritic trunk at some level, but it could be 2 axons. No, I think it has to be 1 axon, but that's the bipolarness is referring to this. Like, there you go, there's a bipolar cell. Yeah, be dendritic and then axonal. The first wave originates in the ganglionic eminence. Eminence, what a great term to use. And this is them leaving as development progresses. The 2nd and 3rd wave come out of the eminences, and that's just generates the majority of the adult ogliodentrocytes, which will create the myelin. And it reminds me of the railroads and how in our brain, there's this genetic, there's a genetic propensity for how these cells are going to go out there in the world, and go out there in the brain, and out into the milieu. But what the brain does, what it needs, that functions that it needs, what it will determine which cells survive and which ones thrive and which ones don't. And a way the best way to think is function structure will follow function. And the reason why I bring up these railroads is because they built these railroads, the initial ones out here, like the transcontinental. It wasn't say, oh, let's build the structure and people will follow. It's because the function was there already. These people wanted to get their goods and services over to the East Coast. And so in the West, connecting the West Coast to the East Coast, it already had people trying to do it by boat or by land like this, like the pioneers here. And that function, that need, structure followed. And you can see the structure continue to follow. The structure still based on what the function, what's needed. Okay, so in myelination, I mentioned earlier, you go 2 miles per hour without myelin, and then it gets up to 260 miles per hour. Plus, you can do a refractory period. You don't have to wait till the message gets all the way out to the end of the dendrite before you're sending another pulse. So it's really can be 3,000 times faster an adult brain fully myelinated in the area where it's fully myelinated compared to a baby brain. You get the fully myelinated is when you have these huge pipelines of 5-micron diameter axons surrounded by the myelin, and that allows that huge fast transmission. And this is looking at the corpus callosum. This is the front of the head up here, and the back head down here with a V. And we get these huge pipes in the back of the head. By the age of about 10 or 11, we pretty much have our adult wiring intact, and for the rest of our life, not counting injury and decline and disease. But the front of the head is going to take forever. Front of the head, we don't get these thick myelinated pipes. They will continue to myelate all the way up to possibly death. See sometimes at 70. There seems to be a decline after the mid 50s and so forth, but a lot of this data is old and pre-iPhone era. So all this information that's available and our ability to use the smartphones to know almost everything we need, keeping that may keep a lot of the myelin going, so that you can have your whole life increasing the myelination in the front of the head. And again, think of it with the myelin, you're going 3,000 times faster than a baby, probably about 30 times faster than a teenager. Depends on what part of the head. If it's the back of the head, you go in the same speed as a teenager. Okay, some other things that come out of Wikipedia. This is just showing that the maturation. The OPCs were long held to function purely as progenitors to the ogliodentrocytes, hence the name. Now they think they have other functions. So the precursors. Some studies suggest that they can become cortical neurons, but other people reject that. And they do some chemical work as well. All right, this is a slide that predates my birth, and looks at myelination that goes on and which systems are getting myelinated the most, and really shows us what's the most important in the beginning of life. Is the most important areas the ones that are already myelinated before you come out of the womb. So the womb, the birth is right there, that line. We have an area of the cerebellum. It's going to be motor function, motor behavior, and then we got the sentinel system. I told you earlier about the sentinel system. Is this one here? It's called in this version statoacoustic tectum and tegmentum. It's they're referring to the inferior colliculus. The tegmentum section would be right below it too. So, okay, so again, it's dealing with acoustic functions. That's precursor to. It's more important to get the acoustic and the motor going before you get the visual and the thinking. In fact, the arousal system, what's called the ARAS, or reticular formation, takes forever to really get close to the adult level, which is one reason you don't want to pause. Oh, how do I pause the recording? Okay, so with the reticular formation, we don't want, one reason why there may be people stunted in the growth when you give them Ritalin or similar kinds of substances is because this myelin system's not ready yet. And they're trying to deal with the stabilization. Actually, I'm mixing two concepts. Let's start this again. Well, one of the things when people are using stimulants to help stabilize a kid's arousal is that the reticular formation is not even done by age 10. So it's not a mature system. So you probably do not want to influence it with exogenous chemicals. And the last thing that keeps myelinating for the rest of our life, hopefully, though there will be a decline, I'm going to show you, is all the connections in our neocortex, association areas. Often there will be a pruning of the cells, and the myelin will be going to those cells that are needed. And it's because of our culture. Like, for instance, there's about 60 phonemes that the human vocal tract can make. Some people may probably argue higher numbers, but 60 seems to be a reasonable number. But most cultures do not use all 60. For instance, in English, we have about 45 phonemes. So what happens, but we have the genetic legacy or heritage to actually understand 60 phonemes soon after we get out of the womb. And when they study babies at like 6 months of age, they can understand all the phonemes. They can detect them even if that sound is not used by the caretakers. Like there's two cha sounds, cha and another one cha. I can't make the different sound because I'm not Inuit. But the Inuit have this two chas, and Japanese, for instance, have trouble with R and L, ra and la, which we may think it's easy, but it is. Those are very similar placements in how we vocalize in our tongue and where the air, how we air it. So a baby can hear all 60, but by about 10 months of age, it will be pruned down to whatever the caregivers around them, that child is speaking. And for like English speakers, it will go down to like 45 phonemes. And what happens, you have this proliferation, all this legacy, creating all this connectivity, but if it's not used, it gets pruned. And this one's actually showing the pruning here. This isn't for the phonemes. This is probably closer to the grammatical and syntactical elements of a language, where we have all these cells and connections that have all forms of syntax. One of the easiest way to think about grammar is where the subject, verb, and object occur. And there's 6 forms or combinations of that. You can be subject, verb, object in your sentences, is the general statement approach in a language like English has. Or you can do verb, subject, object. You can do verb, object, subject, which is, I think that's a very rare one. And again, you just do all 6, the combination of that. So it's subject, object, verb, subject, verb, object, subject, verb, object, verb, subject, and then verb, subject, object, verb, object, subject. It'd be better to see it on a slide, but so those, and they all exist, though I think the object, verb, subject is only in 2% of languages, the rarest one. All right, well, in adolescence, we lose that ability to really be facile with other syntaxes because of this pruning that goes on in specific parts of our head. We have aging functions. We have this proliferation and then a decline. The most interesting area was the superior frontal sulcus area. This is gray matter we're looking at. I mean, like cells and supporting material. Just that it looks like it goes back up. I love that idea. If it truly went back up, it's curvilinear, because it means that there must be some primary function during early years of life. And it takes about 30 to 40 years to be able to feed yourself. We're a very neotenous species. We're very delayed in our maturation, maybe become sexually mature at puberty, or even cognitively mature maybe by our 20s, but at some level, now not all levels. But so there's something being served there, but maybe there's something in our latter parts of life that this is serving. Though there's no real evolutionary pressure once you've already had kids. So once the age of your kids are gone, there's not so much pressure for any system to develop in response to those current problems, like in your 60s and 70s, 80s. Though you can be a grandparent and help, or even a great-grandparent and help your genes survive through your grandchildren and great-grandchildren here. But there may be something. I always love, that's a very interesting idea. The more common one you see is just a decline. Maybe an exuberance, a little bump there, and then a drop. That's the usual one. I probably should have showed this slide just 2 slides ago, because this just shows the synaptic density, and it shows the pruning, and that's probably deals with phonemes. And then there's another pruning going on. That's at 5-6 years of life. And here's the adolescent, there may be even more pruning, and like I said, the syntax area. All right, here's looking at an axon cross section, and this is the central nervous system and the peripheral nervous system. And I'm mostly care about the central nervous system. Look at them all packed in there. This is like connective tissue in here in the peripheral, but this is the central nervous system. They're all packed in, and then when they get that thickly packed, you can get that very fast speed, that 260 miles per hour speed, and there'll be very fast refractory time. Now, one of the most interesting, our brain eventually becomes mostly a glial brain. It becomes an astrocytic and an ogliodentrocyte brain. The neurons, take up less and less of the volume. And the most interesting if you don't count the axons of the neurons in a way that in terms of volume, is this corpus callosum that is the wrapping of those axons wrapped in the fatty sheathing. That's also vulnerable when people get head injury of being cut, because we have this bony thing called a fox that comes in right in that center and can cut, can give us our own split brain sometimes. Here's the thalamus, and here's those colliculi we were talking about before. Here's the thing about the thalamus: it's really only a thin fibrous connection between the two thalami, so they don't communicate with each other really, not directly, I should say. But the neocortex does. About 1% of the cells, neurons in the neocortex has a callosal axon that goes across. But those one cells are influencers. They, in fact, at least seem to be terminating on 10% of the other cells on the other side. And people have looked at, the corpus callosum is very useful, looking at trying to figure out if you can see structural differences that correspond with behavioral ones. And it has different terms here I'm not going to go over. We're going to talk about more when I go into the hemispheres, because that's the most, because this is the communication wiring between the two left and right hemisphere. This is looking at like schizophrenics and controls and Alzheimer's and seeing if there's any changes. That's not really getting me much excitement there. But people do these studies all the time. This one's 20 years old. Okay, this is looking back at the pruning. It's the proliferance and the pruning. And what it is, by the age like 9 or 10, our skull, it seams together, no longer grows. So now we have a limited volume. And in that limited volume, this is showing here, we need more wiring than we need computers. We need more axons and myelin than we need neurons. It's like just like the internet. The internet, you know, computers were valuable on their own when we had SneakerNet. You know, we use a floppy drive, go from one to the other, but not that useful. It wasn't massively useful. They were more specialized, you know, especially in the 80s and 70s. But now with the internet, all that connectivity allows the computer to be all the computers connected on network to be all much more valuable. We need to lose 40% of all, that's supposed to be 40% of all our synapses to cut down the space. What do we need to use? So that's a reduction of 40% of our synapses. We got way too many synapses, and then eventually only have the ones we really need. And this is what I was talking about, how we're largely a glial brain. We got to fill that space with myelin and the other astrocytes and other glia. So that's talking about the 3,000 times the speed. Okay, our white matter peaks. Here it looks like about 45. I'm guessing now 50 or 55 with the iPhone generation going strong here in an iPhone era, let's call it. And because the more you use, you use it or lose it. And the more you are able to be intellectually stimulated, the more you're going to keep the white matter around. But you do see this decline, though there is this variability. That's important. Look at this person here. They're 82 years old, and they look like they're even above they look like a healthy 45-year-old. So you still have those. That's where you want to be, out here. And this is showing the gray matter decline, because the cells we don't need all those cells. A lot of them, they're created, and we don't need to know that phoneme. We don't need to know that concept. We don't need to be able to read in this direction or that direction, or up or down, or whatever. We only need to, for me, for instance, read from left to right. I don't need to read backwards. I can, but my cells aren't well practiced. They're not going to use much material reading backwards. Yeah, for instance, for brain. All right, there's a white matter one I showed you a moment ago. There's a gray matter decline going down, just dropping. And here's the spinal fluid, cerebral spinal fluid, just filling the gap, taking the volume, getting wetter through the decades. If you go to the areas, local ones, frontal lobe, looks like it's peak age of 45. Again, this data is old. It's 20 years old. So again, I would think it's probably going to be more like 50 now. Temporal lobe, if it's going to be 55 or maybe even past that. Again, we want to be out here in the outlier realm like that one. You know, you don't want to be in the under the curve if you can help it. Like this person here is 55, but they got the connectivity of a 20-year-old. We don't want that. Okay. And we can see indirectly the myelination with EEG. This is an early measure. We do a lot of what's called alpha training, theta, the high theta, the alpha range, and co-modulation and coherence does get higher, faster for the alpha range as we progress in age. This is real data. This is ADD individual showing sort of a random, more of a random pattern here. It's a little more linear in the co-mod. And Asperger's, those are Asperger's. Some people think Asperger's are like premature, like they are not prematurely old, prematurely adults. But you can see, look at that low value here in this Asperger. So there's a large range. Better measure of thalamocortical myelination that we do on individuals we do brain maps on, we look at the spectral entropy, and this is a high. When you have someone's eyes are closed and their mind is wandering, you should see an alpha peak. And in the back head, posterior should be largest, but it should progress all the way up to the front if you're looking at entropy. And that's an indication of how much of this thalamocortical myelination. It's a functional measure, so you got to be doing the same task in comparison. This happens to be another, this is an eyes closed, and this is another eyes closed. But if this was like eyes open, these comparisons wouldn't be meaningful. It doesn't, myelin will not change on the person. These are between individual comparison right here. This is one form of measure. This is even, I think, even a stronger form of myelination, or how much, because it's myelination and gray matter. How much governance, how much is the neocortex governing the limbic system? And when you see orange and yellow, orange is the worst color you can see on this map, it means very low myelination, low governance. And when it's blue, it's actually too strong, blocking, too many cells. One of the things years ago, they found out that Einstein, looking at his brain, again, it's like you're looking at a star system way. You're taking little snippets and getting in your electron microscope, or your probably light microscope in this case, and counting things. And you can only do little samples here and there, and they found out that his left parietal had more glial cells. So more support cells, and probably more myelin. I remember the study at the time that they, in the 80s, was it 89 or 86, didn't even really describe what cell type, they said glial cells, but more support. Let's assume also was more myelin in those locations. They looked at the other locations, they weren't statistically significant because they only looked at a few heads. Okay, so we don't have to worry about it through life, is we myelinate, but then you got to worry about demyelination. This is showing a graphic of axonal injury, be it from structural tear, torics. People think a lot of times boxers, having your head move back, or kickboxers having your head suddenly move forward or backwards, those torque forces can damage the myelin and stretch the axons, damaging the myelin. So what's the problem? So when you get demyelination, when your brain starts losing its connectivity, and you have lost that speed of communication, you start losing your short-term memory. That's, you no longer can hold so many elements in mind. Speed is largely intelligence at some level. And when we're talking about someone, that person's smart, that's usually because they have a lot of speed in there and going strong connections means they have a lot of myelin. So with lack of demyelination, with the lack of myelin, the demyelination, you have impaired memory, walking problems, tingling, slurred speech, vision problems, fatigue. It's no longer intact. They're now starting to be tattered. And here's a whole list of demyelinating disorders and causes, from inflammation in your autoimmune system going after your own cells, versus infectious disease, some external, other types of diseases, other disorders, toxic, taking in toxins. Alcohol should be in here, over here probably. Of things that can damage the system, lack of vitamin B12 and some thalidomide, diabetes can cause myelin breakage, reduction. So you demyelinate, you take this thing that's going 200 miles per hour, and now it's going 2 miles per hour. and your train of thought will be also impaired because of that. You won't be able to gather all the forces within. So here we go, Wikipedia again, looking at demyelinating disease caused by genetics, infection agents, autoimmune, and other factors. Here's like insecticides. Vitamin B12 deficiency causes dysmyelination, say there. So, and here comes one, Guillain-Barré syndrome, where you have damage and that results in tingling and loss of coordination. Look at all the things that are going on in demyelination. You can have blurred vision. It can be the source. Demyelination can be the source of it. Ataxia, inability to sort of reach for things, willfully move around. Clonus is rhythmic motions. Dysrhythmia is like, it usually it's an ability to say phonemes well, poor articulation. A lot of times people, you can have fluency problems. Is a fluency in your motor program of organizing all the elements into what you want to say, or is it dysarthritic, if I can say the word? I'm having dysarthritic elements while I'm trying to say it. Very imitative form there, and that would be unable to say a full name. I actually wasn't having dysarthria. I'm having the other version, the fluency problem. So I'm not actually, all the phonemes are fine, I think. Dysarthria, yeah, I can say it. Okay, fatigue, clumsiness, I just had another one. Clumsiness, paralysis, hemiparalysis, or paresthesia, genital anesthesia, wow. That's incoordination, paresthesias, ocular paralysis, impaired motor muscle coordination, weakness, loss of sensation, impaired vision, neurological symptoms, steady gait, unsteady gait, spastic paresis, incontinence, hearing problems, and speech problems. All those because we have myelin or loss thereof. Okay, so how do we remyelinate? Well, let me tell you good news. Neurofeedback. Default network training can do it. We've seen, as I showed you right in the beginning of this discussion or this monologue, this soliloquy, that we can increase the myelin right between the electrodes, where we put it. And there was another study looking at SMR training, and they looked at the myelination of the sensory motor area and the salient network, and they got increased myelin there. I don't think they looked at everywhere. They looked at these limited locations to make sure they had statistical power to be able to find something that was there. And so they show increased myelination with a DTI, diffuse tensor imaging system, after 10 sessions of SMR neurofeedback. There are other arguments or other techniques of how to remyelinate, but neurofeedback is probably the best. There may be some chemical ones, but anything chemical is going to be non-specific. It's going to go everywhere. Here we can target where it needs to go. So this is the study. Never heard of any of these people from Austria. I looked at earlier. Doing SMR study, still doing Barry Sturman's work from which he started in 1967. The default network training is like an advanced form. It's of the OG techniques, the original gangster techniques of neurofeedback. It looks at it's what SMR is really good for motor system situations, issues like hyperactivity and epilepsy. But when you deal with like someone who has anxiety or PTSD or depression, we do what SMR does in the motor strip, we can do everywhere over the head. So we can tackle all the different problems that can emerge. And so it's DNT is an advanced form, you can say, that uses SMR, uses alpha training, has synthesized into an effective way of solving things from attention to memory issues to sleep paralysis problems to epilepsy as well, and depression and mood, bipolar. Okay, but this shows that we can myelinate. Very simple, we can myelinate. All right, this is more of that data of the looking at individuals. They had people who couldn't, with non-responders, they probably didn't have the best system for training. they threw out about half the people saying they were non-responders, and they had data to show why they're non-responders, but that just shows they didn't have a good feedback system. We use movies. We have, almost everyone can be a responder and not be a non-responder. We had one autistic through a clinician friend of mine who just always want to watch the same thing. Don't want to do that because you're not really rewarding the brain, or not blocking the reward when you're with the operant conditioning. You want to be watching new content. It was probably the system was limited. If they did movies technique, they would have gotten all 14 would have been responders. But it's showing where the myelination occurred from the technique. Poor guys, 7 people through who the software was good enough for them to get operant conditioning, but 7 that wasted their time. And here it is. They found their findings were increased fractal anisotropy. Is that how you pronounce it again? I'm having all this dysrhythmia things, or dysarrhythmia. The increased like saturation, in essence, thickness in the cortical spinal tract and the anterior thalamic radiation. And they showed some improvements in cognition. This is a MS group using Nexus out of Netherlands, probably. But it showed there was not when they lose half their patients, that's pretty lame. It's a lot of people, and you gotta have you have the Hawthorne effect. People improve by just watching them. You got the placebo effect. So usually about 30% of people are going to improve just by sitting still, through placebo. Okay, this is going back to the Kaiser study, which is a great study. They were doing a game system in college people, probably very lame games compared to what's out there on your iPhone these days, but you can see that improvement. And it affected like 3 or 4 of these systems with like these fasciculus. They affect the cingulum, the dorsal cingulum. It affected the inferior frontal occipital fasciculus, the longitudinal ones. There's a bunch of them stacked on top of each other, nearby, passing by each other, and improved a great deal. And that was from, I think it was about 30 hours for 30 minutes at a time, 30 visits, 30 hours, 30 visits, half an hour per visit. So after 15 hours, but it was also in healthy people too. Okay, which is actually probably a stronger study than when you unhealthy, because why do you need that extra material for just this neurofeedback? And when you're training, we're looking into doing, when you train someone, you got to look into what's going on in them. And if some people have tingling in the fingers or the mouths, you can put the electrodes right over the motor area to help it, like C2, C1 here, C3, C4, you got it this way. All the way up to C5, C6, which is where we start picking up the auditory off this homunculus. Okay, so just a refresher how we can help myelinate a brain, one that has been demyelinated or is maturing, through just neurofeedback. I guess I can probably start this. This thing probably moves. There you go. And there's a strong correlation with blood flow and EEG, which we use mostly to help explain things to people. We're changing your EEG. That's what we're changing. That's what we're doing operant conditioning on. But the blood flow comes along. You can't have certain rhythms if there's a lot of blood there. If you have a lot of blood, everyone's spinning, everyone's going, all the cells are going wild, doing their own thing, you're going to be desynchronized. If you restrict the blood, very little resources, they synchronize and then go into alpha waves. Things like that. Most patients overthink. We do these brain maps, and they have too much blood flow in the delta range, which is in essence not enough thalamocortical myelin, or not enough coordination. It's a decortication measure, and it's pretty hard to fix, but it can be fixed, and by training. And you also usually have a deficit of alpha in a lot of people too. But that's also thinking too much, putting too much blood flow in the neocortex, not resting enough. The alpha is the resting rhythm, which I've say on other videos if you watch on this this channel, this website. So our goal is getting a lot of the blood flow out of the neocortex, because if all the neocortex has 10 times more cell than the subcortex, if they get all if they splurge, and they get greedy, and they glut out, the subcortex won't have anything. It will have very little, and that deprivation will mean the subcortex will act independent of your desires, or you have moments of fear and panic and anger because it's not following your wishes, your consciousness, when you deprive it of blood flow. And one of the ways to make sure that the subcortex is well fed is by training in this alpha range, usually 7 to 15, 7 to 13. So we do the 6. We're getting the high end of theta there. In the motor strip, we go up to 15 because we're also the alpha range extends higher, or it's mu and SMR in the motor strip. But we're doing that training, and all you do is watch movies. And whenever you're giving us what we want, whenever the EEG is the rhythm we expect, we give you full screen, full volume. That's what this is showing, volume increase. So when you're doing the habit, let's say the habit here is don't overactivate your left temporal frontal lobe here. Whenever you're overactivating it, the screen shrinks, the volume shrinks. And your preconscious system, your brain, not your conscious, not your volitional, but your preconscious will learn that habit. It will be reinforced for that habit, and because it's a healthy habit, once you've gotten your brain practicing this healthy habit, you go out in the world, that healthy habit will help you succeed in the real world. And the DNT, Kaiser DNT, just to make sure, we've been calling it DNT since 2006 when I invented it, has a bunch of tools. So in a way, one of the ways we get our success is we know to exercise the system multiple ways. Co-modulation probably maybe one of the strongest ways. Ceph is great because Ceph seems to work on any channel, and even if you can drive a healthy brain using Ceph, it's not a huge problem. Ceph is a spectral edge frequency. We'll talk about otherwise. These individuals were just analyzing in anesthesia. They weren't using it in neurofeedback. We were the first one to do neurofeedback by modulation. We've been working on for 3 years now. Magnitude has been around since 32. Was even Lord Adrian was looking at like an oscilloscope or equivalent to training his own alpha magnitude years ago, or see if he could. Then again, when coupling's available, we have something called grade, and we have FMT. That one's really old, but they weren't training it back in those days in the 50s, but it's been training since the 80s, I think. Maybe not, 90s. And we got it by a brain map, so it's all personalized for the person, individual. And our goal is to go back up this ladder, go up this slide. So as we get this decline in white matter and gray matter, get us into the outlier level, so your age ain't going to change in a way, but we're going to get you out your outlier so it looks like you belong in this group, the younger group, and increase the white matter and gray matter. And we do it personalized based on what the brain map of the individual shows us. All right. And that is this week's masterclass in ogliodentrocytes.